Welcome to Networks Part 1. Networks, what does that mean? Well, you might think about networking with your friends, solving problems, sharing a math solution on Facebook. That's a bit of a network. What about these guys? What are they doing here? I think they're trying to work out what goes with what to solve a problem. Where do you start a problem? What's the first thing you work out? And then does that lead on and network with another part and so on? That could be important. Do you know of something in sort of modern times now that follow a network? Think about it. Here we go. LAN, local area networks for computers, where you might have a system in a business or even at home where all your computers are linked up. How do you link them up with, let's say, the smallest cable length, so not running all around, but you want them all to be linked? That's the sort of problem we're doing here, and we're going to look at this area of mathematics, which leads on to something called topology. Now, we're not going to do that in this course, but it is a big area of mathematics dealing with solving problems related to many facets or many steps where you're involved in the problem. So let's come down now and have a look at a couple of examples. So over here, you have a friend's place you're wanting to go to. We're calling the person Fan and DN there. And all these connections are the roads that lead from one place to another, and the numbers are the distances. So you could, instead of getting off there and driving or walking or riding a bike, you could sit down and work out the quickest way in terms of Ks to get from one place to another. That's what we're going to use networking for, where we draw a diagram. Here's our diagram with all the connecting points, and then we work out the shortest distance by which we can achieve what we want. What about over here? I think this is a LAN type problem, local area network, where what we're saying here is in how many ways can you connect these computers up? Okay, with the shortest cabling. And I'll tell you now, you might like to look at this one. The shortest cabling to establish this local area network between the 5 purple dots, which are computers, is not the way it is there at the moment. That is not the best way of connecting those computers. And these might be meters, mightn't they? See our problem? What we're trying to do is to work out how to link things up or do a sequence of steps in the best or optimal way. Okay, so we're going to go on and look at some interesting problems that you can use in everyday life to work out the best way of doing something. Come down, and what we're going to do now is look at the jargon or the terminology, if you like, the language we use in this area of mathematics. So first of all, I think you should pause the presentation and make some notes based on these screen clippings here from Hayes and Harris publications there. So first of all, what is a graph or a network? Set of points, some of all of which are connected by sets of lines. Sometimes they won't be. Look at these two here. Because it's not possible to link them. For some reason, there might not be a road there between your place and a mate's place. The points are known as nodes or vertices. That's just language we're talking about here to help us convey to people how we're solving the problem. So here we have edges, which are the lines connecting the points, and they could be undirected. Undirected means you can go either way, and directly connected edges are said to be adjacent. So if you can connect them directly, they're said to be adjacent nodes. So the edges that can connect two nodes directly mean those nodes are adjacent. Okay, now we could use an arc to connect the two lines, and an arc has a particular direction. Okay, so that's different from an edge. Okay, an edge can go either way. Here we are back up here. An edge can go either way, but a arc means it's got some direction. In other words, it's like a one-way street, if you like. You can only go one way up it. Okay, and this is called a directed graph or a digraph. We usually call it a directed graph. Okay, getting used to some of the language because we want to explain to each other what's going on there, and so we have our own definitions in mathematical terms here. Now, an edge or arc, so here's what? That's an edge. There's no arrow on it. Might be given a weight. This may represent the cost, time or distance. Going to a friend's place, you wouldn't go this way maybe because it's 5 kilometres. That sort of thing. So that's called a weight. The degree, we don't usually use valence, or valence of a vertex is the number of edges or arcs which touch it. So this one, how many ways can you get to there? You can go from other points to that point in 3 ways. So you can't reach this vertex at all out here. There are no arcs or edges coming to it. So you've got degree 0. This one over here, a loop, you can go around and come back again, counts as degree 2, but therefore this one's got degree 3, that point, because you can go around and come back to it in some way. Isolated vertex, degree 0. So just watch this here. Now, a loop means you can start at that vertex, go round somewhere, not necessarily to another vertex, no, and come back to that. So it's a loop. Connected graph is one where you can travel from every vertex to every other vertex. Otherwise, it's disconnected. So this one is connected. This one has points, see here and here, disconnected graphs. You can't get to every one via the others. Okay, complete graph, let's have a look now, is a graph in which every vertex is adjacent to every other vertex. Okay, so you can draw a line going, or an arc, or what did we say before, an edge, going from each of the vertices to each other. Okay, so this one is complete. Every vertex is adjacent to every other vertex. Okay, so here this graph is not complete. Can you see why that is not complete? You are not being able to go directly from one vertex to another. The addition here, see this one, would make it complete because the two that were funny here were these two. Did you see that? You can't go directly between those two vertices, or the two vertexes, if you like. The plural of a vertex is vertices. All right, so can you see the difference between those two now? Let's have a look at the last one, definition of a simple graph. What's a simple graph? Well, a simple graph, of course, is one where no vertex connects to itself, and every pair of vertices is directly connected by at most one edge. So this is a simple one. You can't have a loop, in other words. And you can't have 2 ways of going between 2 points. Okay, so mostly we are going to be dealing in this unit with simple graphs. So you're getting some idea of the language of how we're going to be describing what we're doing. Let's get into something more exciting, a bit boring here. Let's go down and have a look at trying to get a little bit more information, but then some problems. Now, what are we going to call a path? A path is a connected sequence of edges or arcs showing a route that starts at one vertex and ends at another. So this is what we're going to be doing, isn't it? This is going to be our solution to the problem of how do we get most quickly to a friend's place, by road or by vehicle or whatever. So that's a path. A circuit is a path that starts and ends at the same vertex. Okay, so a circuit is exactly what it sounds, going around and back again. Okay, and Eulerian circuits. This is not Euler. Euler. How can I put this? Eulerian. That's how we say it. Eulerian circuit. Here's a circuit that traverses each edge or arc exactly once. You don't go over it again. But you do go around all of them. So A to B to C, then back to B here. So you've gone that way to B, then back to B, then to E, then to C, then to D, then to E, then to A. So it's a circuit. You've started and ended at the same point. You haven't gone over any arc or edge more than once. See here, from B to C, you've got two ways. Go B to C and then back to B with the other edge. Okay, so the idea here is just to describe what we're doing. Okay, let's look at a Hamiltonian path. These are named after the guys who did a fair bit of work on this, Euler and Hamilton. So here, it starts at one vertex and goes each to the other, right? But it never finishes where it starts. So it's not a circuit, it's a path. And there we have it, A, E, B, C, D. And that's going to be the likely solution to some of the problems we want to work out. How does a garbage truck, here's a hint, did you think of this? How does a garbage truck pick up all the rubbish in streets without going backwards and forwards too many times? Okay, what's the shortest way of covering that sort of delivery route? Okay, Hamiltonian circuit, I guess you know by now. It starts at one vertex and finishes exactly where it started and visits each one only once. No, if you like, going backwards. No backtracking. Okay, and finally, a spanning tree is a simple graph with no circuits which connects all vertices. So there's a gap here. So called a tree rather than a circuit or a path there that we're talking about. Okay, are you ready? I want you to test yourself on being able to determine what sort of diagrams you've got here. So screen clippings here from Hayes and Harris. And what we've got is, let's look at 7A1. I want you to use your knowledge of definitions. So you might have to rewind the presentation and maybe make some notes so you can check them out. Okay, there's 1 and 2. I want you to pause it, have a go, and I'll show you the solutions down below. Let's go on then to question 3 and 4. Spanning trees, Hamiltonian circuits. Remember what they are. Circuit, starts and ends at the same point, visits each one only once, so no backtracking. Okay, 5 and 6. We'll just leave those answers there for the minute. Okay, see if you can think through those. These are our tools for finding the best way of doing things, or the optimal, what often is called the optimal solution. What's the optimal way of you getting from your place to a friend's place with all the possible routes via walking, bike, bus, or actually getting a lift? Okay, let's have a look at the answers now. Okay, 7A1, here's question 1 and 2. Check those out. Here we have question 3 and 4. And 5 and 6. Okay. Are you getting some idea of how useful this stuff could be? Okay, let's go on now and have a look at something else. Examining network diagrams. Now, you can use networks to display a wide variety of information. We've only done 2 actual examples now, haven't we? Where you're wanting to get to a friend's place or wanting to connect up a series of computers with a local area network. But you could show flow of traffic, or people, or fluid. Which way can fluid flow through a system of pipes? What about this one? This is very important in something called project management. Precedence diagrams. What must you do first and then second? If you're building a new hospital, what do you do first? Can you start putting the bricks down? No, you've got to level the site, look at the plumbing, da-da-da-da-da-da. Oh, that's going to be very important to draw a diagram here. A network diagram. And that's what we're about. So you know what steps can be done first, what others can be done at the same time, and what has to wait until after. What about maps? What we were talking about before, moving from one place to another. Family trees. Displays for sports results. You know, who plays first and the next final, semi-final, preliminary final. They're like network diagrams too, aren't they? Planning out what is the course of the events that are going to happen. What has to happen first, second and third. Are you getting the idea? This is just gearing up now in this first presentation. All right, what I'd like you to do now is to test yourself out. Here's question 1 again from from Hayes and Harris, 7A2. I want you to see if you can work out what they've done with this network diagram. What's it trying to show? Okay. I don't like this language down here. I don't think we should call each other creeps. I think that's very judgmental. She may not like him, but I don't think that's good language. Do you? All right, have a go. Pause the presentation. I'll show you the solutions in a minute. Let's go on now. Question 2, and I think we can get 3 on there. Yep, 2 and 3. Practical problems. How are you going to look at a watering system? How are you going to work out a round robin? Everybody must play everybody, etc. How do you work that out? Hey, this network stuff is quite interesting, isn't it? And quite useful if you've got this sort of problem. Okay, pause it and have a go at those 2. We'll go on now. Oops, there's two other bits for that last problem. So I'll just bring 3 back again. Okay, part F and G are added to that question 3 there. Okay, let's go on. Question 4. Network of his morning activities. Can you see what he's doing maybe simultaneously? What he has to do before the next step and the next step? Okay, it helps to plan out the way of getting through stuff in the right sequence here. Let's have a look at question 5. This is getting between towns now. Okay, what's the aim of this network diagram? Can it help you in real life? I think it can. Okay, pause it, have a go. We'll go on now to question 6. I'll just leave the answers there. And here we are. We are describing the distribution of water in a home, where it flows. You might add weights to this. In other words, 3 things they could represent. If you put a number on that, what is that? That's an edge. No, that's an arc, isn't it? Look at it. It's got a direction. On that arc, what would you say? That's from the water main. The flow. What could you say was what you should put on there? Okay, think about that. There could 3 possible things for each of these arcs here. Okay, let's go on and look at the answers now. So here they are. Question 1 and 2. Some suggestions there. Question 3. All the parts there now. Question 4, 5 and 6. And there we have it. Okay, are you starting to get excited? I think it's a good idea because here it is very useful to actually be able to draw these diagrams to solve actual physical problems in everyday life. Okay, I hope you're enjoying that. There are some more presentations. This leads on to an area called matrices. So let's go on the journey together. But it's cheers for now.